Good morning. Today, we're going to explore a topic that could revolutionize energy use in northern Canada: geothermal energy development. This clean, sustainable energy source has the potential to replace diesel, which many northern communities rely on for both heating and electricity. Diesel is costly, harmful to the environment, and dangerous in sensitive northern ecosystems. Geothermal energy, by contrast, taps into a nearly unlimited source, the Earth's internal heat. So, in this video, we'll break down how geothermal energy works, the different systems being considered for use in northern Canada, the challenges, and the progress we've made so far in implementing these systems. Let's start by looking at why geothermal energy is so important for northern communities. Currently, many remote areas in Canada depend heavily on diesel. Diesel is not just expensive to transport, especially to hard-to-reach areas, it also comes with major environmental downsides. For instance, when diesel burns, it releases carbon dioxide into the atmosphere, contributing to climate change. Additionally, there's always the risk of spills during transportation, which can have catastrophic consequences in these delicate, often pristine environments. On top of that, diesel prices are volatile, which can lead to unpredictable and rising costs for communities already facing significant economic challenges. Transitioning to geothermal energy can provide a more stable, long-term solution. It's renewable, meaning it won't run out, and it drastically reduces carbon emissions, which is a major win for the environment and the fight against climate change. Now, let's take a closer look at the three main types of geothermal systems that could be implemented in northern Canada. Each system has its own strengths and challenges, depending on the specific needs and conditions of the community. First, we have shallow ground heat exchangers. These systems are relatively simple to install and operate, especially in small communities. They're primarily used for heating, rather than generating electricity, but that's already a huge benefit since heating is one of the biggest energy expenses in these cold regions. Shallow systems typically work by circulating fluid through pipes that are buried underground. The ground, even in cold climates, maintains a stable temperature, and this can be used to heat homes and buildings efficiently. The second system is borehole thermal energy storage, or BTES. This is a more complex system that stores excess heat in the ground, usually during the summer months when temperatures are higher, or from waste heat produced by other processes. That stored heat is then retrieved during the winter when energy demand is at its highest. This type of system is particularly effective for smoothing out seasonal variations in energy needs. Finally, we have deep geothermal systems. These systems have the potential to generate electricity by drilling deep into the earth, sometimes as far as 3 to 5 kilometers, to access hot water or steam that can be used to drive turbines. While this approach offers long-term promise, it's also the most technically challenging and expensive. It requires significant investment in infrastructure and technology, so it's likely to be a long-term goal rather than an immediate solution. Let's focus on shallow ground heat exchangers for a moment. One of the reasons these systems are ideal for smaller, remote communities is that they can be paired with solar panels. The panels generate electricity during the summer, which is used to power the heat pumps that circulate the fluid underground. This combination makes the system much more energy efficient, as it leverages the abundant summer sunlight to prepare for the cold winter months. Interestingly, even in regions with permafrost, these shallow systems can still work. Research has shown that with the right design, heat exchangers can be installed in permafrost areas without damaging the ground. This opens up the possibility for many communities in Canada's far north to switch to a more sustainable energy system without significant changes to their landscape. Next, let's talk about borehole thermal energy storage, or BTES. This system has great potential for areas with fluctuating seasonal temperatures. For example, a pilot project in Cujuac, a community in northern Quebec, showed how excess heat from solar panels could be stored underground in the summer and then used to heat a municipal pool during the colder months. This kind of project illustrates a key advantage of geothermal systems. They can be tailored to meet the specific energy needs of a community. In Kuujjuaq, the goal is to gradually reduce diesel consumption, starting with smaller projects focused on heating, and eventually expand to cover more significant energy demands. The challenge, of course, is ensuring that these systems work effectively over the long term. For instance, we need to minimize temperature fluctuations that could affect permafrost stability. There's ongoing research into using vacuum-insulated tubing and other technologies to tackle these issues and make BTES more viable for the North. Now, let's look at deep geothermal systems. These are the most exciting, but also the most challenging, systems because they offer the potential to generate electricity. The idea is to drill deep into the Earth's crust, sometimes kilometers down, to access hot water or steam. That heat can then be used to drive turbines, much like in a traditional power plant, but with geothermal energy, there are no harmful emissions. However, deep geothermal systems face significant hurdles. First, they require substantial financial investment and specialized technology. Additionally, many northern regions have what's called low permeability rock. This means the rock doesn't easily allow fluids to flow through it, which makes it harder to extract the heat. In some cases, we might need to artificially stimulate the rock to improve fluid circulation, a process that's still being studied and refined. While this technology may take 10 years or more to develop fully, it holds great promise for the long-term energy needs of northern Canada. Let's move on to some real-world examples of geothermal projects. In Burwash Landing, Yukon, we're exploring how geothermal energy could be tapped by drilling into the groundwater that flows from glaciers down to nearby lakes. By intercepting this water, we can potentially use it to heat buildings and homes. This project is still in its early stages, but it shows how geothermal energy could become an integral part of life in remote northern communities, even for unique applications like geothermal pools that could attract tourists. In the Northwest Territories, we're looking at communities like Fort Liard and Fort Providence. These areas sit on top of sedimentary basins with high geothermal potential. The challenge here, as with many northern regions, is low rock permeability. That's where enhanced geothermal systems come into play. These systems involve creating artificial fractures in the rock to allow water to flow through, making it possible to tap into the Earth's heat. Though this is a more complex and expensive option, the geothermal gradient in these regions makes it a promising area for future exploration. Of course, developing geothermal energy in the north isn't without its challenges. The extreme cold, the presence of permafrost, and the remote nature of many communities mean that installing and maintaining geothermal systems is no small task. Additionally, there's often a lack of detailed geoscience data in these remote areas, which means we need to conduct surveys, drill exploratory wells, and use creative methods to gather the necessary information before moving forward with large-scale projects. Another issue is the size of many northern communities. With populations often below 1,000 people, it's difficult to justify the cost of large geothermal systems unless they can serve multiple buildings or be part of a district heating system. Still, the potential benefits make these efforts worth pursuing. So, what does the future look like? In the short term, we're focusing on smaller, shallow geothermal systems that can be deployed relatively quickly. These systems provide immediate benefits, especially for heating, and they give us valuable data on how geothermal energy performs in northern environments. Over time, as our understanding grows and technology improves, we hope to expand into more complex systems like deep geothermal, which could eventually help generate electricity. Ultimately, the success of these projects will depend on collaboration between local communities, governments, and private companies. By working together, we can develop the drilling techniques, technology, and expertise needed to make geothermal energy a reality for northern Canada. In conclusion, geothermal energy offers immense potential for northern Canada. It's a clean, renewable resource that can help communities reduce their dependence on diesel, lower their energy costs, and minimize their environmental impact. While there are challenges ahead, the benefits, clean energy, reduced emissions, and long-term sustainability, are too significant to ignore. I'm excited to see how these projects evolve in the coming years, and I hope today's presentation has given you a clearer sense of the possibilities ahead. Thank you for watching.